Okay, so in that last video, you all saw a demonstration of the behavior of arches and chains and the relationship between those two systems. Now I want to show you all my own demonstration just to prove to you that nothing in that video was made up. And also I want to ask you further questions about the distinction between arches and chains. This is an advanced structures course, so hopefully we'll be able to answer more advanced questions about these systems. So here you can see I have a bunch of elements that I've linked together with pinned joints. That is, when I apply twisting motion like this, the pin offers no restraint. It is able to rotate freely about the joint. And so if I hold it up like this, we have a chain. And if I flip it around like this and place its ends into this cardboard here, so I'm applying some boundary conditions, and these would be pinned conditions because I'm giving a vertical reaction against gravity. I'm also providing a horizontal reaction against the thrust of this arch, but there is, again, no restraint against rotation at this joint. And so it is a pinned end. So now if I align this arch properly, you can see that it's able to hold up its own self-weight. However, if I take an external load and apply it at one of these joints, you can see it very, very quickly collapses. Conversely, if I go back to the chain configuration, take it out, and hold it up in my hands, and now I have to do this in steps. I'm running out of hands. If I place my weight here and move my hands roughly as far apart as the boundary conditions in the cardboard, you can see that the chain was able to reconfigure itself and hold up that weight without collapsing. And if I put that weight down, you can see that the chain has now reconfigured itself back to what we saw earlier. See if I can hook the weight here. There we go. So it's able to reconfigure itself. And now if I mirror this configuration back to our arch condition, reapply my end conditions, make sure that it's stable at the ends. And now if I mirror that configuration we saw earlier, so this end was raised up. And now if I reapply the load, really make sure that our ends are stable, now you can see that the arch stands. So now my question to all of you, why is the arch not able to reconfigure itself from its natural position when we apply an external load, but the chain is able to reconfigure itself? And I'm going to give you guys the answer in just a few moments, but I want you to try to think about it yourself. You have all of the information that you need to answer this question. And I'll give you a hint. It has something to do with internal forces and what we learned in week 1 about trigonometry, and what we learned in week 2 about static equilibrium. So if it helps, maybe draw yourself a diagram of each condition with an external load applied at a joint, and then draw the internal forces and the force components in each of these different members. And see if you can come up with an answer to why the tension system is able to realign itself to an external load, but the compression system, the arch, does not.
So let's try to answer this question of why the tension system, the cable, is able to realign itself to an externally applied load, but the arch is not. And let's start with some free body diagrams. Here I've drawn the arch first, so let's start there. So our simplified arch here starts off in a balanced condition. Note that this is not a true arch. We've actually made some simplifications for this demonstration. A true arch would have full curvature along its length from one end to the other, with no bending in any of the elements. Here we have this straight horizontal piece, and so there will be some bending in this piece due to its own self-weight. But we're not concerned about this middle piece for this exercise. We're really only going to concentrate on the two end pieces. We're also going to neglect self-weight for this discussion, as the self-weight of the structure is insignificant and small compared to our externally applied load. So let's look at the internal forces in these two pieces, these end pieces, when we apply an external load. So if we apply a load at the center of this arch, that load would be divided equally between the two end pieces, and it would generate equal internal forces in the end pieces, equal to half of the applied load. So if this were load P, each of these vertical reactions would be P over 2. Looking at our sum of y equilibrium equation, we would see that we have equilibrium here. But we also know that these pieces at either end are pinned at both ends. There's a pin here and pins down here. And so they must start and end with zero bending moment. And if they must start and end with zero moment, and there are no external perpendicular forces applied to them, we know that the moment throughout the member will be zero. In other words, there will be no bending forces in this member. So the forces through this member must be axial. In other words, the internal forces must be aligned with the member. This vertical component we've just drawn is not aligned with the axis of the member. So the total force in this member must look like this, which means that we will have some horizontal component to the internal force in this member. We call this horizontal component thrust. And that's why we need pins at either end down at the bottom here to resist that thrust that's pushing out. So these end conditions must provide restraint in the opposite directions, similar to how they provide restraint against the vertical component. And since we applied the load at the center of the arch, these internal forces, both the y component and the x component, are equal and opposite on both sides. So the thrust on the left side is equal to the thrust on the right side. And once again, if we looked at our sum of moment in the x direction. If we called this one fx, this would also be fx. And so we would have fx minus fx equals 0. But now let's try something different. Now let's try taking this load and moving it closer to one of our sides, rather than placing it in the middle. Now if we consider our internal forces, things change significantly. As we've seen in our free body diagram of beams, more of this externally applied load is going to end up in the closer support. So this reaction here, we'll call it Fy1, will be larger than this reaction on this side, Fy2. And so we have a larger vertical component in this member on the right. A larger vertical component, of course, also means a larger horizontal component, or thrust, as well. Compare that to the other side, which must have a smaller horizontal thrust. So this will be Fx1, this will be Fx2, and Fx1 is greater than Fx2. So now looking at our equilibrium equations, we can see that for the sum of forces in the y, we are actually still okay. Fy1 and Fy2 will end up being equal to P. However, if we look at the horizontal direction, now we have this Fx1 to the left plus Fx2 to the right, and these two are not equal to each other. And so adding them together cannot give us 0. So our structure, therefore, is not in equilibrium. In other words, it is moving. So now let's ask ourselves, how would this structure need to move in order to become stable, to reach static equilibrium? Well, there are two options. Either this joint on the right here moves up, and conversely, the one on the left moves down, or vice versa, where this joint on the right moves down and the other moves up. If this joint here on the right, closer to the applied load, were to move up, then this member on the right would become more vertical, and therefore its horizontal component would decrease. On the left side, this joint would move down, and this member would become more horizontal, and so its horizontal component would grow. And eventually, we would come to a point where Fx2 is equal to Fx1, and we would reach equilibrium. So that actually sounds like exactly what we need. We needed those horizontal components to balance out. And if these joints realign this way, eventually that's exactly what would happen. They would balance out. But there's one small problem with that. In order for this joint to move up on the right here, this heavy weight, this applied load, would also need to accelerate up against gravity. And how often do you see weights move upward on their own? Well, hopefully never, because that's not how gravity works. So the only other option is for this weight to come down until it reaches the ground and the system becomes stable again. And you can see that's exactly what happened in our demonstration. Now compare that to the tension system. Everything in this system is the same. So if I apply this load here, we're going to have some large vertical reaction here and a smaller vertical reaction here, a large horizontal reaction, and a small horizontal reaction. But there is one key difference. Now, for this system to become stable, this joint needs to move down. If this joint moves down, this right piece becomes more vertical, our horizontal thrust decreases. On the other side, this joint moves up, and our horizontal component increases. And eventually, we will get minus fx1 plus fx2 equals 0. We will achieve static equilibrium. And we achieved that with the joint moving down. And so our weight also moved down. It moved with gravity. So in order for the tension system to become stable, the weight moves in the same direction as gravity. Moving in the same direction as gravity is a much easier task for a weight than moving against gravity. And so our tension system realigns itself and becomes stable. Our arch, however, cannot realign itself, and so it collapses.